Hello, this is Brian Rowe, and I will be going over the Physics 1 Lab 1. So the purpose of this lab is to use computational models and compare it to a projected model of me rolling a ball across the screen in this case. And I will be using software such as Tracker, where I'll be able to track the ball moving across the screen frame by frame, gathering data points for my model. And the computational model will be coded using ClosScript, and it will be able to compare my personal observations to the computational models of how it should be going. So there are obviously some fundamental principles, and what we'll be demonstrating is Newton's second law, or the momentum principle. Some useful equations that we can use here is momentum, velocity update, position update, and average velocity here. So there are obviously some initial conditions for the system, and as you can see here, this is the ball, as well as the system, which is, the system is the ball and the surroundings would be everything else. And in the case of this lab, we will be neglecting outside factors such as friction or air resistance. So some conditions are the mass of the ball, which is 4 grams, the initial position of the ball, which is 0, 0, 0, and the initial velocity I calculated by using the formula delta x, which is the distance it traveled, over delta t, which is the time it took to travel that distance. And from that, I was able to get 0.572 meters per second. And here's a video of the ball rolling across the screen. As you can see, using Tracker, the ball was able to be tracked in the center of the mass as it traveled in a straight line here. And in this next slide, you can see that I show the code for the ClosScript for the computational model, where I changed the mass of the ball to 0.004 kilograms, as well as the initial velocity and the time, as well as updating the formulas so that it is a velocity update as well as the position update formulas. And here's the system being run here with the computational model over here with position versus time graph and velocity versus time graph as well. So here is a graph of the computational versus the experimental graph side by side. Obviously, it is very similar as expected, but there are some discrepancies due to the outside factors, which I will be describing in the next slide. So, as I said before, the observed graph is nearly identical to the computational graph with a few discrepancies. So some sources for these discrepancies include improper tracking by the Tracker app, as I had to have track the ball frame by frame, and there could be some human sources of error there. And also there are also outside forces such as friction, possible air resistance, and possibly some dirt on the ground or some obstacles on the ground that the human eye cannot see, obviously. So in conclusion, there are some conclusion questions, and one asked what would happen if the axes were flipped. And this is a good question. Actually, if the axes were flipped, the ball would change in direction to the negative x direction, and velocity would change to the negative, but speed would remain the same. So what this means in terms of the system as a total is that normal force and gravitational force are acting against each other right now, which create a net zero force in the y direction. So there's no movement in the y direction here. But the initial force in the x direction from the push, as well as frictional force that we neglected, work against each other. So it is really hard to determine the total net forces due to the outside factors, as I said, friction and air resistance. Thank you.